looks like our participant list is stabilizing. So, and it's now 3:02 p.m. Eastern time. So I guess we'll get started. Good afternoon, everyone, and good evening or good morning, depending on where you may be, because we have people from all over today. We have some Sumio. You're in Japan, right? He said it's 4 in the morning over there.
Yes, I'm from Japan.
Very nice to have you join us today. And we have people from all over the United States. And of course, our guest speaker today is from the Netherlands. So I would like to welcome Dr. Ben Witvliet, Papa Echo 5 Bravo. He's been a radio amateur since the age of 13 in 1974. He's lived in New Guinea, the Netherlands, Monaco, Israel, Madagascar, and England, where he's held the call signs PA3BXC, PA3BXC/A3A2, 4X/PA3BXC, PA5BW, 5R8DS, and M0IJQ. He loves CWDX, especially on the low bands. He holds 5-band DXCC obtained with 100 watts and simple antennas. Since the beginning of his radio hobby, he has been intrigued by antennas and propagation. He worked in high-power broadcast engineering in the Netherlands and was chief engineer of Radio Netherlands shortwave station in Madagascar, operating two 300-kilowatt transmitters with 17 to 23 dBi antennas. He currently works as a technical expert of the Radio Communications Agency of the Netherlands and continues his research in part-time at the University of Twente. Ben holds his PhD obtained in 2015 along with the Anton Vetter Award for his research on NVIS antennas and propagation. And that's what he will be talking to us today about, near vertical instance skywave NVIS propagation. And Ben is going to explain the propagation mechanism, the related elevation angles, the splitting of NVIS waves into two independent circularly polarized waves, the ordinary and extraordinary waves. And contrary to popular belief, this circular polarization is very important on 3.5 and 7 megahertz. To prove that this is not just theory, he provides elevation angle measurements and O and X polarization measurements. He is going to explain the intriguing happy hour propagation interval, and Ben will also demonstrate through simulation and measurement the optimum antenna height for NVIS is neither as low as possible nor a quarter of a wavelength, and that there is a difference between optimum height for transmission and reception. So this talk will last 20 to 30 minutes, and then we will have questions and answers after. Sound good, Ben?
Yeah, very good. Thank you so much.
All right, take it away.
Let me see if I can share screen. I hope you see my screen now.
Yes.
Okay, good. All right, great to see such a great turn up and all over the world. Respect to our Japanese friend. My name is Ben Witvliet. You pronounce that Witvliet. And of course, you write it in a strange way, but that's because we're Dutch, right? I'm a radio amateur since 1974. I started as a shortwave listener, and I heard about 300 countries on that old setup. But when I went to Monte Carlo for an apprenticeship, I needed the amateur radio to talk home. So I did my, my amateur radio license. I lived in several countries, so I have call signs that match them. The one I'm most proud of is 5 Radio 8 Delta Sierra. If you have that call sign, you don't need an amplifier anymore. I turned my hobby into a career. I worked in industry, government, and academia. In industry, mostly in broadcasting and telecommunications. And I made my hobby my career. So this is the first job I had. It was an apprenticeship in Monte Carlo. On top of that mountain, there is a complete HF station. And on the other side of the mountain, there's a medium wave array with 1.2 megawatt output. And of course, I had my own station with me, PA3BXC/3 Alpha 2. This is a more serious job. Here I was the responsible of the station, the chief engineer, with all Malagasy staff. Very nice to work there. We had two 300 kilowatt AM transmitters and high gain antennas, and my call sign was sufficient to call once and then listen for half an hour to the people shouting. So I enjoyed it quite a bit. When I returned in the Netherlands, I worked for the Netherlands Broadcast Transmitter Company. This is one of their towers. It's higher than the Eiffel Tower. We had 6 of them. And we also had a bunch of medium wave stations. And at Christmas, the one that's in the center of Holland near Utrecht has lights in the stay wires. So it becomes a Christmas tree that you can see 50 miles away. Already since quite some time, I now work for the Radio Communications Agency in the Netherlands. And firstly, mainly on applied research, now also in advisory functions and standardization and spectrum management. This was a very nice job that we did. We built a measurement system that's that's a colleague of mine and myself. We designed and built a measurement system to fly around VHF FM broadcasting towers to measure the antenna diagram and calibrate its EIRP. And at some point, when you get bored, so you have to find a new challenge. So I did my PhD in part-time, starting in 2011. I started on a different subject, but the work that we did on NVIS was more successful, so I switched to that, and I promoted in 2015. And that's what I'll be talking about. The outline of this talk will be first on the ionosphere, then on several aspects of ionospheric radio wave propagation, and then on how to match the antenna to the propagation, which is important. I prefer to take the questions at the end. Please watch the right-hand lower corner. It has numbers. Those are the slide numbers. If you remember them, we can quickly skip back to the slide that you have questions on. But let's start at the beginning. We live somewhere close to the surface in the troposphere, and most of us don't come higher than about 10 kilometers. But the atmosphere goes higher up, and the ionosphere, the ones that we radio amateurs cherish, is somewhere between 60 and 1,000 kilometers. It's sustained by the radiation of the sun. Different wavelengths come deeper or less deep in the ionosphere, in the atmosphere, where it ionizes a part of the molecules and atoms that are over there, and they've free electrons that are free to roam around. Those electrons are not uniformly distributed over height. There's a peak height, and there are several small irregularities in the profile. This is just a sketch of the profile. It's different every minute of the day, and it's different at different places at the Earth. Inside that plasma, because such a cloud of gases that has a lot of free ions is a plasma. There are those free electrons that oscillate around their position, mechanically oscillate, and they have their own frequency, and that frequency depends on the density of electrons. Why is that important? Well, if we send a radio wave straight up, it reflects at exactly that position where it finds a plasma frequency that's equal to the transmit frequency. So that's here you see the same curve, but now calculated for plasma frequency. So on the horizontal axis, you now see frequency, and you see familiar values. If you send a radio wave up, it will be reflected at some point where it finds that the plasma frequency is sufficient. And if we would do that for a lot of frequencies that are slightly increasing, you see the following profile starting. See a jump where that shape is retreating. And at some point, the frequency will become so high that it does not find a matching plasma frequency anymore. And it goes through the ionosphere into outer space. Okay, we could draw a line through all those reflection points. And as most radio amateurs recall, it looks like a layer. It looks like a layer that is frequency dependent. It has some cutoff frequencies, and it has a more or less fixed height. Well, not really, but it looks like that. The critical frequencies are for each layer. So for the E layer, it's FOE. For the F2 layer, it's FOF2. And there are several small variations of that as well. But there are no real layers, as you've seen. There's a continuous profile of electrons. There's just only some bending points that have these effects. So there's a region in which refraction takes place. And the lowest one is the D region, which is so dense with neutral atoms that it only absorbs radio waves, mainly at the lower frequencies. Then we've got the E region and the F region. If we transmit above the critical frequency of the F2 layer, all the waves that are vertically emitted go through the ionosphere and get lost. But at a lower angle, they still have time to gradually refract back to Earth. And you have a coverage area that may be very far away. So that's what we DXers generally use. But at a shorter distance, you don't hear anything. It's a dead zone or skip zone. It's different if you stay below the critical frequency of the F region, because then even for vertical emitted waves, you will get a reflection, and you have a continuous coverage area that starts straight at your transmitter. And this is ideal for humanitarian organizations that work in, for example, the inlands of Congo or other regions where there's no communication networks. And it's also ideal for emergency communication, for example, after Hurricane Katrina or something similar. This is near vertical incidence skywave propagation. So it's almost vertical that the wave enters the ionosphere. The signal strength in that coverage area is almost independent of distance. So completely different from VHF, where the signal strength diminishes very quickly with distance. And all the rays are coming seemingly from one point high up, which also defines one of the other aspects of NVIS. If you are in between steep mountains, you will still hear the signals. The elevation angle depends on frequency. On lower frequencies, you will have the E region reflect. On high frequencies, you will have the F region reflect. And somewhere in between, you will have breaking in the E region and then a reflection on the F region. It can also be seen in these simulations. These are a lot of ray tracing simulations put in a graph. On the horizontal axis, you see the distance. The vertical axis, you see the elevation angle. And then you see multiple lines. And on the right-hand side, you see the frequency going up from 1.5 megahertz to 6.5 megahertz. The red traces are pure E layer reflection. The green ones are F layer reflection. And the blue ones are a mix between the two. This is at the sunspot minimum, so at a sunspot number of 10. And if you would select one of the highest frequencies that still has NVIS possibility, in this case 5.5 megahertz, and you take the size of the Netherlands, which is 170 kilometers radius, you come up to 70 to 90 degrees elevation angle, so pretty steep. Of course, I did these simulations also for a sunspot maximum at an SSN of 120. And then the highest frequency that works nicely is about, what is it, 10 megahertz, 9.5 megahertz. I selected 7 megahertz because I used that in a lot of experiments. And again, you see that the elevation angle is between 70 and 90 degrees. Of course, these are simulations, and simulations are never good enough to represent nature. It's only a simulation and a simplification. So we did measurements. At the work, we have a professional direction finder, which gives 3D direction, so azimuth and elevation angle. And we used a Dutch amateur radio contest in which people are obliged to contact each other to do those measurements. So we did 2 hours of measurements. We measured 85 stations, about 200 measurements in total. And we verified the location of each of the stations. That was done very easily. We calculated the azimuth angle to their given location, their formal location. And then the ones that were not in that direction, we just called them at home and asked them where the hell they've been last weekend. And they were generally quite astounded. We knew they were not at home, and the radio agency made a good impression that way. But we corrected all the data, so this data set is clean after this verification. And these are the measurements plot in a graph. So horizontal is distance again, vertical elevation angle, and each dot presents one measurement. And it gives a very good agreement with simulations. You also see the ground wave, and on the left side, which is 0 degrees elevation, you see a couple of values that are a bit off, a bit awkward, because they're between 0 and a higher value. And that's because there's interference between the ground wave and the sky wave. And it was quite astounding. This is on 7 megahertz. Any station further away than 20 kilometers, so 50 miles or so, came in via skywave. So far in all those pictures, I've pretended that there was only one wave traveling in the ionosphere. However, we know better already since 1931 because Appleton did interesting experiments. He transmitted the signal over, I think, 35 kilometers with a pulse transmitter. And at the receive end, you see first the ground wave coming in, and then the F1 and F2 layer reflections. This is on a borrowed cathode ray tube. They were not that common at that time. But he also did experiments with circular polarization, and he found that the first reflection was right-hand circular and the second reflection was left-hand circular. And that led to his magneto-ionic theory and the formula for refraction. A very simplified explanation. If you have a plasma and an Earth's magnetic and a magnetic field, in this case from the Earth, and you transmit a wave into that plasma with linear polarization, it breaks up internally, and only circular polarized waves are able to propagate within the plasma. And as they have different refractive indexes, they will follow a different path. So you have two different rays coming out of that block of plasma, one with left-hand circular polarization, the other with right-hand circular polarization. And if you do a ray tracing simulation through the ionosphere and make sure that both waves end at the same point at a certain distance, you see that the left-hand and right-hand circular polarized components follow a completely different path, which also means that the delay will be different and that the attenuation will be different. And if the delay on that path is varying, it will be varying differently for both of them. You also see that the left-hand circular polarization, which is the ordinary wave, is highest. It's also the one that pierces the ionosphere first. So also their critical frequency is not the same. So we have two different critical frequencies. The FOF2 is a parameter that most DXers know. That is the critical frequency of the F2 layer of the ionosphere, the highest layer. But that's for the ordinary wave. So the O is for ordinary. So that implies there must also be an FX F2, which is the extraordinary wave. And that's true. It's generally in the ionosondes you find it as FXI because it's the highest frequency of the ionosphere. So it's the cutoff frequency for the X wave of the ionosphere. This leads to very interesting phenomena. These are ray tracings over part of a day. This is in the morning in the Netherlands on 7 megahertz in 2014. At 6 o'clock UTC, both waves will penetrate the ionosphere and disappear into space. Then at 6:30, the sun is up and heats the ionosphere. And the ionization becomes sufficient to reflect the extraordinary waves first, because that one has a different critical frequency than the ordinary wave. At that moment, you will only receive right-hand circular polarization. That's on the northern hemisphere, but the whole audience is from the northern hemisphere. So this is an interval that I dubbed happy hour, because there was no name for it yet. And each time that we demonstrated this worked, we were dancing because the equipment was good enough and we had it done. And the name stuck. So happy hour it is. After half an hour in the morning, because that goes pretty rapidly in the morning. Also, the ordinary wave is starting to reflect, and both waves will arrive on the ground. At 11 UTC, the ionization has increased, so the reflection point has lowered. At 1500, it's almost the same. But then at 2030, the sun is already down quite some time in the Netherlands. We have sunset in March, I think at 6 o'clock or 5:30 in the evening. That means that the reflection point will be quite high, and also that the ordinary wave again pierces the ionosphere. So again, we have only right-hand circular polarization. Until an hour later, both waves will pierce the ionosphere. Of course, this is a strange effect that we only could deduct theoretically and by simulation, so we wanted to see it. So we made a setup in which we transmitted linear polarization. And on the receive end, 110 kilometers away, we put up a turnstile antenna of which we could switch this phasing between left and right-hand circular polarization. By the time I didn't have my SDR yet, so we used an expensive receiver of the radio agency controlled via LabVIEW software. And that software also switched the phasing unit. This is the antenna at a nice, quiet rural location to have the best signal-to-noise ratio possible. And this is one of the recordings. This is the first day of measurement, 24 hours. You see in the top graph, let's display talk about the top graph first. The red trace is the ordinary wave, and the green wave trace is the extraordinary wave. You see when the band opens up, the signal increases 50 dB. We still hear the signal at night too, but that's because of scattering. It is about 10 to 15 dB above the noise. But when the propagation opens up, that adds 50 dB. You also see two intervals, one here in the morning and one here in the evening, where the on-off switching of the ionosphere is different for both polarizations. So right-hand circular polarization lasts much longer. In the evening, it's about 3/4 of an hour. And also after that, you see a gradual decrease of the signal after the switch off, which is scattering, which becomes less and less. In the bottom graph, you see a mathematical difference between the signal strengths of the two. That's just to confirm that those two waves are completely independent. We measured 25 dB of isolation, but that's probably the maximum we can make of cross-polarization with this turnstile antenna. And this is the second day. You see that it's similar but not identical. You see that here the evening happy hour lasts much longer, but the effect is the same, and also the isolation is almost the same. So what if we want to match the antenna to the propagation? Well, the experiments I just shown prove that both waves are quite isolated. which also means that if you want to get rid of polarization fading, so the fading that's caused by the interference of both characteristic waves, you have to switch to your antenna to circular polarization. And that may be either on transmission, you will then excite only one of the waves, or by reception, where you only will receive one of those waves. Of course, you can make something much nicer if you have a dual circular polarization receiver. You could do that with a turnstile and a dual channel SDR. And then in the digital domain, you can make the phase difference for left and right hand circular polarization. And those two channels will then be completely independent. So that makes for a perfect diversity system to combat multipath fading. So very good for emergency communications or for contesters that do in a local contest. And this is for NVIS propagation at frequencies below 10 megahertz. It's also on 3.5 megahertz. I have a colleague, PA0, Shara India Mike, who does experiments with circular polarization as well. And you see the same effects on 3.5. Now, what polarization do I use for the antenna? Well, not vertical. So if you use a vertical antenna, it will have the diagram that's below it. And it will have a very steep null at the angles where NVIS propagation starts. If you have a horizontally polarized antenna, however, you generally have a maximum even when that antenna is close to the ground. A few simulations, so this one should not be used. There are a lot of myths about antenna height. The most common one is that NVIS antennas must be as low as possible, then you will have maximum gain to the zenith. Won't give my opinion yet. I will just give the answer in a scientific way. The second one is, well, if the first one is not true, then it's at least true for receive antennas because they're so much quieter if you put them on the ground. And then the third one is generally from the scientific people. They say, no, it has to be absolutely a quarter wavelength above the ground because that's the height at which the ground reflection reinforces the ray that goes straight up. How do myths come to be? Well, very easily. A person has an opinion, maybe by trying something once. He shares that opinion to, he or she shares that opinion to a group. The group reverberates that same opinion. And after a while, everybody says, well, I heard that, and that becomes the new truth. But that's why we have science. These are simulations first. This is a half-wave dipole antenna above farmland ground at 0.02 lambda. When we increase it to 0.06 lambda, you see the gain increase quite a bit. Then to 0.2 lambda, it's still a higher gain at the angles that we need. But then if you go higher still, the gain will still increase, but not for the angles that are useful for NVIS. There we have the first problem. Antenna gain is generally defined at the angle where radiation is maximum. So we cannot talk about antenna gain anymore for this question. So I adopted NVIS antenna gain, which is the average antenna gain between the angles that are useful for NVIS. Of course, because I'm living in the Netherlands, and also consider this for humanitarian applications. It's for short range, so up to 200 kilometers. And then 70 to 90 degrees is the range to consider. If we do put those simulations in a graph, you see the blue graph for antenna gain. And you see it drop down quite a bit at low angles. It's different for directivity. So if you would not consider the losses, but only the antenna diagram shape, it would be the green graph, and it would have a fall off after 0.05 lambda or so. And red graph is the ground loss calculated from the difference between the two. So the maximum gain would be here for transmission, that is. Of course, that was for farmland. You can also simulate it for clay and for sweet water. That's the middle big arrow. Then for urban ground, that's much drier because of all the pavement. So there the height will be slightly higher. And for seawater, which has a very good conductivity and a very high epsilon R, it will be a bit lower. Again, these are simulations, so verification by measurement is needed. So we put up a beacon transmitter at that time at 5.4 megahertz. And we put up several antennas with a computer-controlled switch, and again, the same expensive receiver. This is a picture of the situation. The antenna heights, the antenna height in wavelength, and we used F2 propagation. These are the measurements. So if you take these measurements during a full day, and you plot all the individual signal strength points as a continuous line, as a histogram actually, but I put a line through it. And you do that for the different antennas. You see these graphs. So the optimum is between the antenna of 0.16 and 0.22 lambda. And if you go low, if you go to 1 meters, you lose about 12 dB. So that's a very stupid idea. If you need the antenna for emergency communications, it will work. So it's good to get quick contact. But as soon as you have the chance, raise the antenna to the proper height, and you'll gain 12 dB, which is substantial. So with that, we solved the myth that the antennas must be as low as possible. You also see that the antennas are not always at 0.25 lambda above ground. It's even ground dependent. So two myths solved. We still have the question on receive antennas. Will that be the same height as for transmission? Well, it doesn't look like that. If we simulate the directivity of the receive antenna for different ground types, you see the optimum is much lower. It's around 0.08 lambda. And of course, directivity is the same as signal to noise ratio if the radio noise or the interference is uniformly distributed, which we don't know. So again, we did the same experiment. And we plotted the results, and we see the results are quite different from transmission. So we have now the optimum is just slightly lower than at transmission. It's now 0.16 lambda. And also the 1 meter height is not 12 dB down, but only 3 dB down. So it's much less critical on reception. So apparently the losses we have by lowering the antenna are compensated as well by the selectivity of the antenna, the directivity of the antenna towards where the noise is. And it's apparently not uniformly distributed, because otherwise the optimum would have been very low. And this remains interesting as long as I don't have a directional antenna to measure where the noise comes from. I cannot answer what's the cause of this. But at least this myth can also be stricken off our list. Okay, I've in the presentation I put references so you can read them at your own leisure. It's easy to get the publications because they are on a ResearchGate, and I'm ready to take any questions.
Thank you very much, Ben. It's wonderful. Any questions?
Yeah, Ben, I have a question. What ray tracing program did you use? Just as an FYI.
Yeah, I have been using PropLab Pro version 3.
Okay.
Up to 3 years ago or so. I also have FarLab now, which is much nicer because it's MATLAB driven. So all those graphs that you saw about the NVIS elevation angle, I've done by hand, and then put them in an Excel sheet to get those nice curves.
Oh, very,
That's a lot of work, and it's because of PropLab. It's primitive in its interface.
very nicely done.
Hi, Ben. I have a kind of a theoretical question on, you say use a turnstile antenna to get circular polarization, right? Correct?
Yes.
I was wondering what in your opinion, what would be the effect of if you were using Yagis to transmit, say tribanders up at a quarter to a half wave height? What would be the effect of tilting the antennas, tilting the driven elements so they are no longer parallel with the ground? What kind of polarization would that give you, or would it even be noticeable on the receive end?
Okay, you ask a couple of things, but I first need to know, are you using them for DX or is that for NVIS? Because that makes a difference.
Well,
for
actually,
DX.
it's a combination. It's for like for an example for field day where you want to work not real big DX, but you want to work one hop and you want to work a lot of local stuff too.
Yeah. Okay. Very, very clear. Well, first of all, as long as the elements remain horizontal themselves, if you tilt the antenna upwards to improve the radiation at the angle that you prefer, maybe 30 degrees, 40 degrees, something, you still remain horizontally polarized because that's just defined by the elements themselves.
Okay, but you're talking about tilting the boom upwards, correct?
Yes.
I'm talking about rotating the driven element. So I'm sorry, I might be getting ahead of you. But, I was going to say, instead of tilting the antenna up like this to raise the takeoff angle, if you will, I'm talking about rotating it like this. And I'll get to why I want to do that in a minute. But I was just curious as to what your opinion is of what that would look like on the receive end if you did that on the transmit end.
Let's first talk about what you are transmitting, because what you see on the receive end is something different. So what you are transmitting will be partly horizontal and partly vertical if you do that. And both the components will have a different vertical radiation diagram because the ground is acting differently on them. So where there's a minimum on the vertical component, there's a maximum on the horizontal component.
Kind of like a sloper antenna.
Yeah, it's unfortunately the way that nature does that the ground reacts. So if you, it's just even the same on VHF. We had a problem like that measuring polarization on 50 megahertz sporadic E. It's very important that you look at the ground effect. But let's assume that both horizontal and vertical polarized components have an angle at which they are approximately the same. Then they go to the ionosphere, but it will still be a linear polarized wave because the phase angle between them will be constant, probably be even the same, be 0. And then you have magnetoionic splitting, and it will be just the same as if you have any other linear antenna.
Okay, so what I'm hearing is probably no effect at all on the receive end.
Yeah, except that you change your vertical diagram, so you will have a null filler. If you have a horizontal antenna, you will have, and you are high enough, you will have multiple lobes. If you then tilt the antenna 45 degrees, you will have a null filler because the vertical components will fill the zeros in your vertical antenna diagram.
So actually, for mixed DX, it might actually work out better than strictly horizontal or strictly vertical.
It could, yes.
And you see what Go ahead. What I'm trying to do is I'm trying to get the driven elements of two close-in antennas perpendicular to each other, so I can get some kind, and I think that will work. I get some kind of null. So for a two-station contest station, if you will, you can get some nulling effect without having to move the antennas way far apart or move them vertically separate. And I don't know if that'll work, but I was just curious as to whether you actually even see much on the. I guess you will, but it might end up being a benefit to you because it may fill in the lobes, which is what you want for me anyway. You want to get as much coverage as possible. You don't want to skip over people.
Yeah, I understand that.
Anyway, thank you. Very good presentation.
Oh, thank you, Scotty.
So Ben, I have a question.
Yeah, go ahead.
Yes, so I noticed some of your antennas were flat, you know, so they had a constant height above ground, and some of the turnstiles I think that you showed had inverted V,
Yeah.
where the ends sloped. So can you talk about the difference in performance? So this would be gain of holding a constant, let's say 0.18 wavelengths above the Earth versus the inverted V. You know, I'm assuming, and please correct me if I'm wrong, that the flat antenna has higher performance.
Yes, and it depends. But it's not a nice answer, of course. I never simulate. I haven't simulated yet a whole bunch of inverted V's, because inverted V antennas are very practical also for my experiments, because you only need one mast. And if you want to have a very well-defined turnstile with horizontal dipoles, you need 5 masts, because you also need to support the cable and the balance. That being said, I think if you would raise the inverted V a little bit higher than your horizontal dipole to get the same effective height, you will have almost the same gain. You will always lose a little bit because of the angle between the two legs. It's of course always best if that's 180 degrees, and any angle between them will lower them. But the difference is not that dramatic. So as long as the angle between the two legs is 120 degrees or more, it's almost perfect. It depends if you want to gain the last 0.2 dB or so.
Right. And so let's, I have one last question here, and this deals with the difference in gain performance for NVIS of a flat dipole, single dipole at 0.18 wavelengths versus the turnstile with, so it has a 90-degree phasing line in it. And depending upon which one, it's right hand and left hand. Tell me about the difference in gain of using a circularly polarized turnstile versus just the simple flat dipole.
Yeah, and then it's then you. And I assume you look end to end, so up to the receiver, right?
Yes.
Okay, that means we have an antenna, which is the most important message I like to get across anyway. You have the antenna, you have the propagation, and then you have again an antenna, and that whole system is your propagation path. So it depends what propagation you have. During the morning and evening happy hour, it's only right-hand circular polarization that propagates. So if you could transmit with the matching polarization, you would always be stronger, because you would be losing power on a single dipole, 3 dB power, and now you're matching it fully, assuming that you have very low loss in your phasing unit. You will have best matching, so you will be 3 dB stronger. If there's if both waves propagate, it's a different story. Then it's not then with circular polarization, you will only have half of the propagation possibilities in the ionosphere. So you lose 3 dB of what you can get across the ionosphere. But then again, at the receive end, you will introduce a lot of fading. Because at the receive end, if you have a linear polarized antenna, which most people have, you get both waves, left and right hand circular polarization at the receive antenna, but they will have a random phase and a random attenuation between them, and they will add up and produce random polarization again. And that means that you have fading all over the place because of rotation of the polarization, which can be quite rapid depending on the path length difference between the two, which will generally be more than 1 wavelength. And then if it varies, you will have a very fast phase shift between the two. So there it's more important to look at fading than to the absolute signal strength, because the absolute signal strength, you're talking about 3 dB plus or minus. Then on the fading, you have notches that are 20, 25 dB down. And there on reception, if you want to have best reception, you would have to make a dual turnstile, either two turnstiles with opposite polarization and a dual receiver. Or what I would do, I did it on transmit side, so it can be done on receive side. You take a double SDR receiver with two synchronized receivers. For example, AN200D or maybe one of the flex radios. And then after that, you in the software, so you stream the signals to your computer. And in the software, you make the phase difference between the two dipoles. And you make two audio channels, one with left hand and one with right hand circular polarization. You only need one inverted one turnstile antenna for it. You just, you don't need any phasing. You do that in the digital domain. And then if you put them on your ears, you will hear the strangest variation from left to right. And if you make a diversity system to keep the highest amplitude of the two and suppress the other one, you have a perfect diversity system. And that will cancel a lot of fading. So not only the polarization fading, but also the normal multipath fading.
So in the first case where you feed one to each ear, say, then you're using the brain to combine them and pick out the one with the least fading.
Yes.
As opposed to using the computer to combine it into one signal.
Yes, and that will work. In England, I only worked 50% of the time, so I was flying back and forth. So I didn't have a big station there, but I had a loop antenna and a vertical antenna, a quarter wave vertical antenna for 40 meters. And I always put one on my left ear, the other one on the right ear. And that was mainly because there was fading difference on 7 megahertz DX, but also interference difference on both of them. And it works.
Thank you, Ben. Great presentation.
Good, thanks.
Ben, I did have one question about your slide number 27.
Okay.
On how you measured the elevation angle.
I'll go there. How I measured that. This is equipment that cost about 1 million euros. It's two turnstile loops, if you wish. There's phasing for circular polarization in each loop, and there's 9 of them. This is primitive to what can be done, but then it's more expensive still. It has 3 digital synchronized receivers. It switches between the first 3 elements, then the second 3 elements, then the third 3 elements, etc. And for each of them, it calculates from the phase difference between correlated signals, what is the 3-dimensional direction of the wave. And with all of them, it gets a better fix and also a quality figure. It's completely automatic. It's meant to be a single station locator, so it gives azimuth and elevation. And we were just looking at the elevation for this graph.
Okay, thank you. Great presentation. Thank you.
Thanks.
Hey, Ben, I have a question about when you were talking about the different types of ground composition, and you said that it looked like C, you could keep your antenna a little bit lower. Have you ever thought about, I've thought about this before, like what, would you be able to keep a lower antenna if you put like basically like a reflector along the ground, like something conductive to kind of mimic that?
Yes, of course. It's also I've visited a naval station in Portugal, and it was a tour from the UCAP conference, and they had several antennas on that terrain. They had for NVIS, they had crossed log periodics that were pointing straight up, but they also had a kind of a wideband spiral antenna, a multiband spiral antenna, that was sitting only 10 meters above the ground, but the entire ground was one big earth screen. So that's a very effective way of doing things. Of course, I worked in broadcasting, so on medium wave transmitters, we also had 120 radials of 2 lambda, but that's not for the general radio amateur, and especially not for humanitarian organizations or for emergency communications. So there you're very limited. If you want to make a ground screen, it has to be much larger than the antenna, at least a quarter wave larger than the antenna. If it's laying on the ground or very near the ground, it's not tuned, or it's very difficult to tune. So it's not very easy to make a good ground. The only way would be to put a lot of copper in it, like meshed copper or a radial system or something similar. And then I would say
Okay.
it's easier to put up 2 or 3 turnstiles, put them in phase, and you have more gain as well.
Okay. Great. That was a great presentation. I appreciate it. Thanks.
Thanks.
Thank you very much. Those are all really good questions. Are there any more questions for Ben today? If not, Ben, I want to thank you very much for joining us today and giving us this wonderful presentation. I think it's great, and it's certainly an area of interest that really, I think, touches on many people who are hams interested in propagation, scientists who are interested in the ionosphere, and EMS and emergency communicators and defense people who are interested in more tactical types of communications. So thank you very much.
Yeah, you're welcome, and thanks for giving me this audience. I enjoyed it a lot.
I'm so glad. And we're going to have you back again in 2 weeks on November 12th, and you'll be talking about radio noise. Do you want to give us a preview of that talk?
Well, I can tell a little bit about it. I still have to combine the slides from different things I have and make a few new ones, just like I did today. Of course, for radio amateurs, the noise level is very important. You cannot hear anything that does not come above the noise. But it's also for other professionals. In the International Telecommunication Union, I'm in the study group 3, who is producing propagation models for frequency planning mainly, but also the radio noise models. And there have been measurements way back in the 70s or even earlier, also in the USA, that defined the radio noise levels. And especially the man-made noise level, so what is above the natural background noise. But since then, there's been very few measurements. It starts again in the last 20 years that in the UK, in Japan, and in Germany, there have been measurements done. But the interest is, of course, shifted to the higher frequencies. Everybody tries to make money with large bandwidth. And that means that the domain at which you have world communications is a bit neglected. And then at the same time, EMC emissions are highest at lower frequencies. So what I've been doing in the past and what I'm still doing is measurements of radio noise. And I would like to present a little bit about that with the challenges you have to build equipment, especially to measure the quiet rural levels, so the lowest levels, and also give a status update of what's already done in the ITU and what's still missing. And maybe I can inspire people to do radio measurements all over the world again, because only measurements in the USA, in Germany, in maybe the Netherlands, and in Japan does not represent the entire world, and the ITU does.
That would be excellent, then. Thank you very much. Well, I think we are coming close to our 4 p.m. Time slot today, so I'm going to close the official part of this HamSCI Telecon for today. But I'll leave the channel open for now. So anyone who'd like to stay on and chat for a little while, you are more than welcome to. I'm probably going to have to go do something in the room in a couple minutes. So if I dash off, that's why. But yeah, please feel free to stay on and chat. And thank you and have a great day. 7-3.
Thank you, Nathaniel.